You ever stop and think about how a beam of light can actually cut through solid steel? Or how a giant magnet can literally see inside your brain? These things aren't magic tricks. Not at all. They're what happens when we harness the most fundamental and sometimes, the most bizarre laws of physics. Today, we're going to pull back the curtain on the invisible science that powers just about everything in your world. I mean, really think about that for a second. Light. We think of it as gentle, right? Something that just illuminates a room. But somehow, we figured out how to concentrate it with such unbelievable precision that it can reshape a human eye or slice right through metal. So how on earth is that even possible? And it's not just light. We've also figured out magnetism on this massive, massive scale. We're not just talking about sticking a note to the fridge anymore. We're talking about generating these just breathtakingly detailed images from deep inside us, all without making a single cut. It sounds like something straight out of science fiction, but it's happening in hospitals every single day. But nope, it isn't magic. The answer to both of those questions, of course, is physics. More specifically, it's our deep understanding of things like quantum mechanics, electromagnetism, and nuclear physics that has totally unlocked these incredible abilities. So today, let's dive in and explore some of those hidden laws. Okay, first up, let's tackle that crazy beam of light, lasers. They're absolutely everywhere, right? From the barcode scanner at the grocery store to your Blu-ray player. But how they work, well, that's just a beautiful piece of quantum physics in action. So the whole secret to understanding a laser is actually hidden right there in its name. See, laser is an acronym, and it's basically the entire instruction manual for how to build one. It stands for light amplification by stimulated emission of radiation. Let's break that down. It really all boils down to 3 key steps. So first, you have what's called spontaneous emission. Imagine an atom with a bunch of extra energy, it's excited, and it just randomly spits out a particle of light. Okay, fine. But here's the clever part. If that little particle of light hits another excited atom, it stimulates it and forces it to release a second identical particle of light, a perfect clone moving in the same direction. To get that powerful beam, you need a chain reaction. And that's where step 3, population inversion, comes in. You have to engineer a situation where you have way more excited atoms ready to be stimulated than you have calm, resting atoms. And you know what? It all comes down to this simple-looking formula. This is basically the on-off switch for the whole thing. N2 here is just the number of your excited atoms, and N1 is the number of atoms in their normal resting state. For that laser to gain power and actually fire a beam, you just need N2 to be bigger than N1. That's it. The gain has to be positive. And when you master that one principle, look what happens. This perfectly controlled, amplified light is what carries our data across oceans and fiber optic cables. It's what welds car frames together with mind-boggling precision. It performs LASIK eye surgery, and it even helps manufacture the very computer chips we're going to talk about in a minute. So, okay, we can control light using quantum physics. But what happens when we start applying similar ideas to the atoms inside our own bodies? Well, that brings us to our second technological marvel, magnetic resonance imaging, or the MRI. To really get a sense of the power we're dealing with here, just look at this comparison. A fridge magnet is strong enough to line up a few little metal paper clips. An MRI magnet, on the other hand, is powerful enough to reach inside your body and align the protons in the hydrogen atoms of your water molecules. I mean, the difference in scale is it's absolutely staggering. So this whole process is called nuclear magnetic resonance. First, that monster magnet aligns all the hydrogen nuclei in your body's water. They all point in the same direction. Then, the machine zaps them with a quick radio pulse, which knocks them out of alignment. And as they relax back into place, they give off this tiny, faint signal, like a little echo. The MRI machine is basically just a giant, super-sensitive antenna, listening for millions of those echoes. Okay, so how does a machine turn a bunch of echoes into a perfect picture of your brain? It uses this principle called the Larmor frequency. The best way to think about it is like this. Every type of atom responds to a very specific note, just like a tuning fork. So by slightly changing the magnetic field across your body, the MRI can play different notes and then listen for the echoes that come back from specific spots. This is how it can tell the difference between bone and fat and muscle, because they all echo back just a little bit differently. Of course, turning all this amazing physics into a real medical device takes some incredible engineering. You need these superconducting magnets that are cooled to almost absolute zero. You need precision gradient coils to do that spatial mapping we just talked about, and you need these highly sensitive radio frequency coils to send and receive the signals. It really is a symphony of physics and engineering working together.
So we've got lasers manipulating light, and we've got MRIs manipulating atoms. So what's the common thread here? Well, both of them are direct results of the single biggest shift in physics in the last 100 years, the quantum revolution. And it turns out this revolution is responsible for, well, basically all modern electronics.
Yeah, the heart of every single computer chip relies on this one quantum idea, the band gap. Think of it like an energy hurdle that electrons have to jump over. In a conductor, like a copper wire, there's no hurdle at all. Electrons just flow freely. In an insulator, like rubber, that hurdle is way too high. They can't jump it. But a semiconductor, that's the Goldilocks material. The hurdle is small enough that we can give the electrons just a little push to get them over. And that ability to precisely control the flow, to turn it on and off, that is the foundation of every single transistor. But then it gets even weirder. See, down at the quantum level, electrons don't always play by the rules we're used to. Sometimes they don't even need to go over the energy barrier. Thanks to this totally bizarre effect called quantum tunneling, an electron can just disappear from one side of a solid insulating wall and reappear on the other without ever having enough energy to actually cross it. This ghost in the machine isn't some weird curiosity. It's a crucial part of how modern electronics actually function. So let's just be really clear about this. The billions of transistors, those tiny little switches that are powering your computer and your phone right now, they're not just microscopic versions of a light switch. They're fundamentally quantum devices. Their entire operation depends on the precise quantum-controlled flow of electrons, governed by these strange principles like band theory and tunneling. Whew, okay, so we've seen how physics discovered a century ago literally built the world we live in today. So how does this all come together now, and what does it mean for where we're headed? Just think about the device that's probably in your pocket right now. Its microchips were etched into existence using precision lasers. Those chips contain billions of those quantum transistors, and its ability to communicate relies on the fundamental principles of electromagnetism. Your phone, it's a perfect integration of every single concept we've talked about today. It's this monumental engineering achievement that literally puts the laws of the universe right in the palm of your hand. And you know what? The story is so far from over. The same deep understanding of physics is now powering the next huge wave. Quantum computers that manipulate individual atoms directly. Photonic circuits that use particles of light instead of electrons. Even more advanced medical imaging systems. They're all being built on these exact same foundations. Look, the story of modern technology really is the story of physics. By daring to explore the unseen rules of how the universe works, we unlocked the power of the atom and we completely reshaped human life. So the real question isn't if physics is going to enable the next great leap forward. The question is, what will that leap be, and what hidden corner of the universe will it reveal to us next?